Hello, everyone. Welcome back. This is going to be the fourth and final part of our linear algebra review series. We're going to begin with vector norms. A vector norm is a quantity that describes the size of a vector. There are many possible ways to do this, but the three most popular are the one norm, the two norm, and the infinity norm. The one norm, to get that, you take the absolute value of every entry and you sum them up. The two norm, also called the Euclidean norm, you take the absolute value of every entry, you square it, you sum them up, and then you take the square root at the end. Somewhat analogous to the traditional distance formula. Lastly, the infinity norm is simply just the maximal absolute value of each entry. In general, a norm can be any sort of rule as long as it satisfies these properties. It has to be non-negative. The only vector of length 0 has to be the zeroth vector. It has to behave the correct way with respect to scalar multiplication so that the norm of alpha x has to be equal to the absolute value of alpha times the norm of x. And it has to be subadditive. This is a property called the triangle inequality that says that the norm of x plus y must be less than the norm of x plus the norm of y. And depending on what norm you use, you're going to get to a different intuition about what the size of different vectors are. So to illustrate this, I'm going to consider unit vectors. That's the vectors with norm 1 for different norms. And you can see that for the 2 norm, the set of all of the unit vectors, it looks like the traditional circle. On the other hand, for the 1 norm, you get this diamond shape, and for the 2 norm, you get like a box. Matrix norms are the matrix counterpart of vector norms. They're also denoted by these double pipes like that. And any matrix norm must satisfy the following four properties. It's still required to be non-negative, with 0 being the only matrix with norm 0. Similar property with respect to scalar multiplication and the triangle inequality. And the new one is the submultiplicative inequality, that the norm of A times B must be less than or equal to the norm of A times the norm of B. Importantly, every vector norm induces a matrix norm, which for the norm of A that's induced by the vector norm is going to be the maximum over all vectors with length 1 of the length of A times X, the norm of A times X. Or equivalently, you can use linearity to write this as the ratio between the norm of A times X divided by the norm of X. Intuitively, this should be thought of as how much does this matrix stretch out or shrink a given vector. For the one norm and the infinity norm, there are simple formulas. It turns out that the matrix 1 norm, you take the L1 norm over of each column, and you take the maximum one of those. A infinity, it's the same thing, but with the rows. So the A infinity matrix norm, induced matrix norm, is the max of all of the 1 norms of each rows. For the 2 norm, we need the concept of a spectral radius. So the spectral radius of B is going to be the largest eigenvalue and absolute value. And you can compute the 2 norm of a matrix by taking the spectral radius of A star A, where star is the conjugate transpose, and then taking the square root. To illustrate the 2 norm, I'm going to consider this picture here, and I'm going to assume that A has kind of sheared the system so that now we get an ellipse. And the length of this black arrow is going to visually be giving you the norm that's induced by the 2 norm. The other most common norm that's not an induced norm is the Frobenius norm. And essentially what the Frobenius norm is you take A, you reshape it into a big long vector, and then you compute the vector 2 norm. Or equivalently, you take each entry, you take its absolute value, you square it, you add all those up, and you take the square root. And lastly, we're just going to note some useful inequalities involving matrix norms. Any matrix norm is bounded below by the spectral radius. The norm of A times X is always going to be less than or equal to the norm of A times the norm of X for the induced norms. The and then there are some relationships between the one norm and the two norm, between the two norm and the infinity norm, and the two norm and the Frobenius norm, or the two norm and the one norm and the infinity norm. Not much to say about these other than to pause for a second and let you read them. And that's where we're going to stop.